Good afternoon. Thank you for the introduction. My name is Raul Múñoz. I am the head of the Packet Optical Network and Service Research Unit at CTTC, and I'm going to present this paper that is entitled Dynamic Reconfiguration of WDM Virtual Network Topology over SDM Networks for Spatial Channel Failure Recovery with gRPC-telemetry. It is a joint work in collaboration with KDDI Research in Saitama, Japan. This is the outline of the talk. First, I'm going to briefly introduce the paper. After that, I will also present the targeted scenario and the proposed SDN control architecture. Then I will also show the workflow and the specific algorithms that we have deployed for dynamic reconfiguration of WDM VNTs for spatial channel field recovery. And then after that, I'm going to show the experimental activities and results that have been performed before concluding the paper. The traffic carried in the transport networks has been continuously growing over decades. The current research goal is to deploy 1 Mbps per second optical transport system with 10 terabits per second optical line interfaces to meet the future traffic demands. A novel optical network architecture that has been proposed to increase the capacity of the optical network systems is the spatial channel network. Basically, a spatial channel network is composed of spatial cross-connects that enables to provision spatial channels that occupies the entire available spectrum of a conventional single-mode fiber or one core in a multi-core fiber. Multi-core fibers can be carefully designed to suppress the crosstalk between cores below the level permitted by the transmission system, allowing spatial cores to be individually switched. A spatial channel network allows to bypass the overloaded WDM networks by provisioning a spatial path between WDM nodes, following a similar strategy as done for IP over WDM. We presented for the first time the concept of SDN-enabled WDM virtual network topologies, VNTs, over SDM networks in the ECOC 2021 paper. In this paper, we proposed an experimental validated reconfiguration of SDN-enabled WDM VNTs in response to spatial channels failures. This feature is very important because it enables to restore failed virtual WDM links instead of restoring the optical channels at the WDM layer. We consider a WDM over SDM physical network that is composed of ROADMs and optical cross-connects that are connected to spatial cross-connects. So we can dynamically provision spatial channels between ROADMs, and these spatial channels are considered virtual WDM links in order to provide WDM VNTs networks. Spatial cross-connects are equipped with optical performance monitors, such as optical spectrum analyzers, to measure the parameters of the optical channels, for example, the optical signals to noise ratio. We deployed a spatial cross-connect telemetry agent for each OPM to stream the measured data to the WDM over SDM orchestrator via a gRPC interface. The WDM over SDM orchestrator is based on the micro ABNO that was developed by CTTC, an SDM controller built using a microservice architecture. So given the modularity that the microservices provide, it is easier to develop new functionalities, deploy it on the cloud computing service, and scale the different modules depending on the load. To support the creation of WDM VNTs, we already proposed a WDM VNT manager microservice that was responsible for the provisioning and removal of WDM VNTs. In this work, we extend the WDM over SDM orchestrator with two additional microservices as shown in the picture. On the one hand, a spatial cross-connect telemetry collector for collecting the streaming telemetry data using the gRPC, and also a spatial cross-connect degradation analyzer for the single-mode fibers and core link failures. Now we show the proposed workflow for reconfiguring a WDM VNT. First, the network operator defines the logical WDM VNTs. So basically that means they involve physical WDM nodes and the virtual WDM nodes, and then it requires the deployment to the WDM over SDM orchestrator. We skip all the details on how a WDM VNT is provisioned because they were already provided in the previous paper. So once the WDM VNT is deployed, the spatial cross-connect telemetry collector subscribes to the spatial cross-connect telemetry agents to get the telemetry data for the provision spatial channels that are used in the virtual WDM links. So this is the first subscription. So then the telemetry data is processed by the spatial cross-connect degradation analyzer to detect failures in single-mode fibers or spatial cores in multi-core fibers. To avoid false alarms, the spatial cross-connect degradation analyzer also needs to get in real time the list of active connections in the WDM VNT SDN controllers. So in another paper, we presented an streaming telemetry, a streaming mechanism for optical network based on the Kafka architecture and protocol. It basically enables an efficient distribution of the state and network updates following the ONF Transport API streaming implementation agreement. So that's why we can also subscribe to this information to the SDM controller. So once a single mode fiber or the core failure is detected, the Spatial Cross-Connect Telemetry Degradation Analyzer notifies the WDM VNT within the SDM orchestrator. It identifies the failed spatial channel and asks for its removal to the connection microservice that will send a request to remove the associated SDM TAPI connectivity service to the SDM SDNS controller. So this is the first action that is performed here. Then the topology microservice requests the context to the SDM SDN controller to update the available resources. And after that, the WDM VNT recomputes a new spatial path for the failed virtual WDM link, and then the WDM over SDM orchestrator requests the provisioning of the SDM TAPI connectivity service to the SDM controller, specifying the compute spatial channel. And finally, the WDM SDM orchestrator also retrieves the resources from the SDM layer. This is the routing and spatial assignment algorithm that we are proposing for restoration of degraded virtual links. So first we try to compute another spatial channel using the same route as the one that was used in the degraded spatial channel. So to that end, we compute first what are the available single mode fibers or cores on all the links along the same route, and then we allocate the single mode fibers or the core on each link of this route. In the case of single mode fiber, basically we just allocate the first one that is available on each link, and in the case of the multi-core fiber, what we do is to compute the set of continuous cores that meet the spatial core continuity along the route. So that means that the same core must be available on all the links along the route. So then for each continuous core, we calculate the overall occupancy rate and select the core with the smallest overall occupancy rate, aiming to avoid the crosstalk effect. So this overall occupancy rate is computed in this way. So let's consider, for example, that the continuous core is the number 1. This continuous core has as a neighboring cores number 2, 14, 13, and 12. So then what we do is for all the links and for all the neighbor cores, we compute the occupied spectrum and also the supportable spectrum in this way. And then of course we select the one that with the smallest overall occupancy. So in case that we cannot manage to find an available route, an available single mode fiber or core in the same route as the degraded one, what we do is to compute a new set of route. So using, in that case, a cache shortest path algorithm that minimizes the number of hops. And of course, here we also remove the route that has been used in the degraded spatial channel. Then we take the first route and allocate the single mode fibers and the cores following the same procedure as in the step number 2. In the case that the single mode fibers or the cores cannot be allocated, we can repeat that for the second route that has been computed in this cache shortest path. And then, of course, in the case that there is no available route, then we return an error. The experimental setup is based on the WDM over SDM orchestrator, a WDM VNT SDN controller, and also an SDM and SDN controller deployed at CTTC in Barcelona, in Spain, and then also a WDM over SDM physical infrastructure, and as well as also the corresponding SDN hardware agents that are deployed at KDDI Research in CTM in Japan. The SDN controllers and the agents were connected using OpenVPN tunnels on top of Internet. The WDM over SDM infrastructure was composed of 2 ROADMs and also 4 transponders that were connected through an SDM network domain. This domain includes an 11 kilometers 90 core multi-core fiber with fan-in and fan-outs, and also 2 fiber switches. The spatial cores are monitored by an optical spectrum analyzer that measures the optical signal-to-noise ratio of the optical subchannels. We also introduce a variable optical attenuator to degrade all optical channels within a spatial channel. So this is the experimentation that we have carried out. So first we have created a WDM VNT that was composed by two ROADMs, ROADM number 1 and number 2, that were connected using a special core, in this case number 3. And this VNT, WDM VNT, was also composed of 4 transponders. Then we also dynamically provision 4 digital signal rate connectivity services at 200 gig per second between the transmitter and the receiver of the 4 transponders. So in this figure, we can show the histogram of the provisioning time of these DSR connectivity services. And we can see that it takes around 38 seconds that are consumed mainly by the hardware configuration. So that means by the ROADMs and the transponders. The WhatsApp shows the packet capture from the WDM over SDM orchestrator after the WDM VNT has been created. The step 1 correspond to the subscription of the to the Spatial cross-connect telemetry agent by means of a gRPC stream just after the creation of the WDM VNT. And in the step 2 shows the OSNR data sent by the telemetry agent every 3 seconds that is configured by default. Finally, the last figure, this figure shows the initial OSNR data that is sent by the Spatial cross-connect telemetry agent for the 4 optical channels that are associated to the provision digital services at 200 gigabits per second. The second test that we have carried out is the recovery of the provision WDM VNT. We generate first a spatial channel failure by adjusting the BOAS to introduce an attenuation of 30 dB to all optical channels. And once the OSNR degradation is detected, we trigger the recovery of the failed virtual WDM link. So here we show the watershed capture, where you can see all the different steps that are performed by the WDM over SDM orchestrator. So in the step number 3, the orchestrator removes the SDM TAPE connectivity service, so the spatial channel, through the core number 3. In the step number 4, the WDM over SDM orchestrator requests the TAPE context, so the topology and resources to the SDM controller. Then after that, in the step number 5, the WDM over SDM orchestrator computes a new spatial channel using the core number 6 and requests the provisioning of this spatial channel to the SDM controller. Then in the step number 6, the WDM over SDM orchestrator requests the TAPE context to the SDM controller. And once the virtual WDM is restored, the telemetry agent starts to send the new correct OSNR values using the new spatial channel, as you can see here in this figure. So the overall time for recovering the virtual WDM link is around 15 seconds. So conclusion, the deployment of WDM over SDM will require new SDM control solutions to efficiently manage the spectral and spatial resources, providing spatial channels between ROADMs in a similar way as done for AP over WDM. Virtual WDM links can dynamically be deployed between ROADMs to provide additional spectrum to cope with the traffic growth in a link or to offload some ROADMs. We have demonstrated the feasibility of the dynamic reconfiguration of WDM VNT. The experimental validation has shown that the failed virtual WDM link can be recovered in just 15 seconds, that it is half of the time that will be required to restore the optical channels, that is in order of 38 seconds, that are employed in the provisioning time, considering both the transponders and the ROADMs. So that's all on my side. Thank you very much for your attention, and now I'm available for questions.